Alright, in this video we're going to practice some of the math skills that we need for our forces unit. Some of these we've actually already practiced in other units. So for example, splitting vectors into components. We've done that with velocities and other vectors like that. We can do it with forces too. So here's a force. It has an x component, that's the horizontal component, and a y component. So just like our kinematics unit, it's going to be really important to draw that coordinate system. And then you can split forces into their components. We're going to do this a lot. So here's the x component of this force. That's called Fx. And here's the y component of this force, that's Fy. Important thing to notice, I put arrows on the components. It's really important for them to have a direction. That direction is going to tell you what their sign is as well. So for example, Fy is down, right? So it's going to be a negative sign. Okay, to get the values of these, I can just use Sohcahtoa. If you remember from kinematics, we learned a short form for Sohcahtoa for when we're splitting things into x and y components. You almost always know the hypotenuse, right? That's the force you're given. You're trying to find either an adjacent or a opposite side. And the trick that I used is that cos is close, so the side close to the angle is going to be cos. The side far away from the angle is sine, because sines are kind of far away on the highway. So that's sort of my quick mnemonic for doing Sohcahtoa in this specific situation. So Fx is going to be 4.52 cos 30, which is 45.2 cos 30, 39.1. The units of that are newtons, and it's positive because my Fx is forward, so that's positive there. Fy is far away from my angle, so it's going to be sine, so it'll be negative because it's down. 45.2 sine of 30, which is going to be 45.2 sine 30 is negative 22.6 newtons. Awesome. Alright, now that we practice that, we're going to do our bigger goal here, which is finding net force. So the symbol for net force is the sum, so it's our sum symbol, of the forces. This is really important to be good at finding net force because the main equation, not only for this unit, but actually really for all of physics, arguably one of the most important equations in physics, is that net force is equal to mass times acceleration. So being able to find that net force in all kinds of different situations is going to be a really, really important skill. So what you'll see is basically a dot that represents some object, and it'll feel a bunch of forces, and the forces will be shown by arrows pulling in all different directions on that dot. And our goal is to add up all of those force arrows to get a net force. But you can't just add up all the numbers. You have to add them as vectors. This is a skill you'll use in math. If you take calculus and vectors, you'll use the same skill of being able to add vectors, which don't add like regular numbers. So how do you add vectors? What you first do is you find all the x components and the y components of every force. So that's what we were just practicing here. Any force that's at an angle, we're going to split into x and y components. That's our first job. Once that's done, we find all the x components and we add them all up to get the net force in the x direction only. And then we look for anything that's in y and we add it up to get the net force in the y direction only. Once we know net force in x and net force in y, we put those together to get the net force. And we can't just add them together either. We add them as vectors because Fx will be horizontal. This will be the net force in x. And Fy will be vertical. The net force in y will probably look something like that. And so my overall net force will be this guy, something at an angle like that. So I'm going to use the Pythagoras Theorem because it's a right angled triangle to get net force. And I'll have to use Sohcahtoa to get that angle as well. Okay, that's the process. Let's see what it looks like with an easy one. So this one is easy because all the forces are either in x or y. So you can see I've got my coordinate system here. Y is positive up, x is positive forwards. So no forces are at an angle. So my first step of splitting forces into components, I don't have to do. I can jump right to the second step of summing up forces in x and y. So the forces that are in the x direction, I'm just going to list them. There's F1, and really important when you're listing these forces to get the sign right. So use your coordinate system to make sure you're doing the sign right. So F1 is in the x direction and it's positive 7 newtons. F2 is also an x direction force, but it's backwards, so it's going to be -3 newtons. F3 and F4 have no components in the x direction, so I don't need to write them down here at all. In the y direction, so if I sum up my forces in y, I have this F3, which is +1, and my F4 is down, so that's -4 newtons. All right, so I've listed my Fx forces, listed my Fy forces. The next thing I just have to do is add them together, sum those all up. I get the net force in x is going to be the 7 plus the -3, which gives me -4, or +4, sorry, newtons. I'm still asleep here. Here we've got the net force in y, I've got my +1 Newton, I've got my -4 newtons, so overall my net force in y is going to be -3 newtons. There we go. Okay, so I've got my net force in x, I have my net force in y, I need to put those together using Sohcahtoa. Here the sign matters again in terms of how I draw my picture. So Fx is 4 newtons forward, right? It's positive. So this is the net force in x, is 4 newtons, and it's forwards. But Fy is -3 newtons. So from here, I have to go down -3 newtons. So Fy is -3 newtons. And what I'm trying to find here is my overall net force, which is this guy. That is my net force. That's my goal, to find that one. So first I'll get the value of net force, and for that I'm going to use Pythagoras Theorem because this is a right angle triangle. I can do c squared here, which is the net force, is going to be a squared plus b squared, those two sides squared. So I'll have net force. It's going to be the square root of the fx squared plus fy squared. Plugging in the numbers there, it's the square root of 4 squared plus 3 squared. It's a -3, but it doesn't matter at all for this. It's going to get squared anyway. Oh, we don't need to calculate for this. That's 16 and 9. It's 25 underneath there. Square root of that is 5. So we have 5 newtons. So our net force is 5 newtons. The next thing it needs is an angle. So you can find either angle that you want in the triangle, it doesn't matter. Maybe I'll find this one, but you could also just as easily find the one at the bottom, that's fine. So theta, we're going to use Sohcahtoa for that, and tan of theta is going to be the opposite, so that's the 3, divided by the adjacent, which is the 4. And to get the theta out of the tan, I need to inverse tan it, so it'll be the inverse tan of 3 over 4. Putting that into my calculator, I'll have inverse tan of 3/4. That gives me an angle of 36.9. So theta is 36.9 degrees. Actually, I only have 2 sig figs. I need to round that off. So theta is 37 degrees. All right, so I have my angle, and I have my net force. So we're done. All right, let's do an example with a force on an angle. So here's one where we have to do that first step. Our first step is splitting everything into x and y components. So F1 is fine, it's in x perfectly. F2 is fine, it's perfectly in y, but F3 is off at a funny angle. So our first job is to split it into an x component this way. And make sure you put that arrow on it, right, because this is overall backwards. So this is F3x, and a y component like this. That's F3y. Okay, so let's calculate what those are. F3x is going to be negative because it's backwards, and our x is positive forwards, y is positive upwards. So F3x will be negative. It'll be negative 3.1. It's close to the 30 degrees, so it'll be cos of 30. I'm not going to have room there, so I'm going to write it down just over here. F3x is going to be negative 3.1 cos of 30 is 2.685. Just keep a few decimals for now. We'll round at the end. That's probably fine. Okay, F3y over here, that one is far away from my 30-degree angle, so it's going to be sine, and it's actually also negative, right? Because F3y is down and y is positive up. So it'll be negative 3.1 sine of 30, which is, so 3.1 sine 30, negative 1.55 newtons. That's F3y. Alright, so I split every force that needed splitting into components. My next job is just to sum up all the x stuff and sum up all the y stuff. So sum of the forces in x here and sum of the forces in y here. So in x I have F1, and that's forwards in x, and it's positive 2. So F1 is positive 2 newtons. And then F2 has no x component, so I don't need to write anything down there. F3 has one x component here, and that is the negative 2.685. So F3 in the x direction only is negative 2.685 newtons. All right, y direction forces, there's F1 has no component, there's F2, and that's up, so it's positive. So F2 is 1.9 newtons. And then there's F3y. This component right here is in the y direction, and that is negative 1.55 newtons. Our next job is just to add up x stuff and add up y stuff separately. So some of the forces in x is going to be the 2 plus the negative 2.685. This is where it's so important to get those signs right? Otherwise you get completely different numbers. That'll be negative 0.685 newtons. And in the y direction, net force in y sorry, is 1.9 plus the negative 1.55. And that's positive 0.35 newtons. Okay, I've got my net force in x, I have my net force in y. Next what I need to do is just put those two together in a nice little picture. So x is actually backwards, so I'll start by drawing that one. So this is my net force in x, and it's a negative 0.685 newtons. And then this is my net force in y. Net force in y is positive 0.35 newtons. And what I'm trying to find here is this, which is the overall net force. I can use the Pythagorean theorem for getting net force here. I'll do that up here. So net force is going to be the square root of the net force in x squared plus the net force in y squared. Plugging in my numbers there, that's going to be the negative 0.685 squared plus the 0.35 squared. And let's see what that gives me. So 0.685 squared plus 0.35 squared. Square root all that, and I get 0.77. It looks like I want 2 sig figs here. Everybody has 2 sig figs, so I'll stop there. So there's my net force. I also need an angle, so maybe I'll find this angle looks like a nice one in here. So you could do that one, like it doesn't matter actually which one you do, just as long as you indicate on your picture which one you're planning to do. So that's the angle I'm going to do here. And I'll use TOA for that. So tan theta is the opposite. That's this side here. So that's the 0.35 divided by the adjacent, the 0.685. I just need to inverse tan this stuff to get the theta out. So 0.35 divided by 0.685, and then inverse tan that, and I get an angle of 27 degrees. And that is my net force with its direction. All right. So one last example, just for good measure, of lots of forces here on our object. I took out force 1 because it was just too many. So we have force 2, 3, 4, and 5. Same process works, right? It doesn't matter how many forces you have. So our first goal is just split any forces that are on an angle into their components. So here is F4 in the y direction, and it's up. So this is F4y. And then here is F4 in the x direction, and it's backwards. So don't forget those arrows on it. That's F4 in the x direction. And we'll start by calculating what they are. So using our trick, cos is close and sines are far away. So this guy here, F4y, is close to the 11-degree angle. So I'm going to use cos. So I'll do the hypotenuse, 4.2 cos of 11 degrees. And it's up, so that's going to be positive there. So let's calculate that. 4.2 cos of 11. That gives me 4.1228 newtons for F4y. And for F4x, it's going to be negative, right, because it's backwards. The hypotenuse, 4.2, and the sine of the 11 degrees. Sines are far away, if you want to remember that trick. So it'll be 4.2 sine of 11. That gives me 0.8014 newtons. Great. There's one other force we need to split into components. That's this guy right here. So it'll have an x component here and a y component like this. So this is F5 in the y direction. This is F5 in the x direction. In the x direction, if I do my cos is close rule, right, that one's close to the 35-degree angle, so it'll be 2.1 cos of 35. That's going to be positive because it's forward. I'll plug that into my calculator, 2.1 cos 35. It's going to be 1.7202 newtons. And in the y direction, this will be negative, right, because this is down, so negative 2.1. And it's opposite the 35-degree angle, so sine of 35. Plugging that in, I have 2.1 sine 35. And I get negative 1.2045 newtons. That's my F5 in the y direction. So just notice, sometimes people get into a habit of sort of thinking that x is always the cos one and y is always the sine one. Notice how that's true here, right? X happens to be cos, the y component happens to be sine. But here the y component is actually cos and the x component is sine. So don't try and use that as a mnemonic or a rule to remember. If you want to use rules to remember, either use Sohcahtoa or use the cos is close, sines are far away. Either of those is fine, but don't think x is always cos and y is always sine. That's not true. It just depends on which angle you're given, right? If I was given this angle, x would have been cos, but I was given this angle. So that means x is sine. Okay. We've done our first bit, which is just splitting everything into components. Next, we need to write down all our x forces and all of our y forces. So some of the forces in x first. What have I got here? So F2 is in x, and all of it's in x, and all of it is backwards, right? Always remember your coordinate system. X is positive forwards, y is positive upwards. So I need to write that down as a negative 1.9. So F2 is negative 1.9. F3 also fully in x, and it's backwards, so that will be negative 6.1. F4 has an x component. We just calculated it. It's backwards, and it's that negative, oh, I forgot to carry my negative through, sorry about that, negative 0.8014. So negative 0.8014 newtons. F5 in the x direction is forwards, and it's that 1.7202. Great. Next, some of the forces in y. So look at all the y direction stuff. F2 has no y component, nothing pulling you up and down there, right? It's just horizontal. Same idea with F3. But F4 has a y component, so F4 in the y direction is positive 4.1228. And F5 has a y component, and that one's down, so it's negative 1.2045 newtons. Awesome. It's a good idea at this moment just to pause, quickly check through, do I have the right signs? Because a sign error at this stage leads to huge mistakes, and it'll totally throw off your number. So just check. F2 is backwards, negative. F3 is backwards, negative. F4x is backwards, it's negative. F5x is forwards, it's positive. F4y is up, it's positive. F5y is negative because it's down. Okay, good. So just a good idea to do a quick double check on that so you don't make a mistake with your signs. All right, then we add up all of our x stuff and all of our y stuff. So we add up all these forces in the x direction. So the net force in x is going to be just add those numbers together. So I'll start with my negative 1.9, oh sorry, negative 1.9, add negative 6.1, add a negative 0.8014, add a positive 1.7202, and I get a net force in x of negative 7.0812 newtons. Do the same thing with y here. So the net force in y is going to be these numbers added together. So that's my 4.1228 plus the negative 1.2045. And that gives me 2.9183 newtons. Great, so I've added up everything in x, added up everything in y. My next step is to combine the net force in x with my net force in y. So I draw a little picture. Net force in x is a backwards negative 7, so that means I need to draw a backwards arrow here for that. It's a backwards force. So that's my net force in x of negative 7.0812. And my net force in y is up, it's positive. And that Fy is 2.9183. Great. What I'm trying to actually solve for is the overall net force, so that's this vector. The overall net force here, that's just going to be Pythagoras' theorem. You'll sort of notice in these sorts of problems, you do the same thing at the end a lot, right? Like once you found fx, fy, it's basically always the same pattern. We need to use Pythagoras' theorem to get net force. So that's going to be the square root of fx squared, or the net fx, plus the net fy squared. Putting in our numbers, that's going to be, x here is 7.0812 squared, y is 2.9183 all squared. Toss it in your calculator. Oh, sorry. Square the, I have the y in there already, it's kind of handy. I'll put x in there too. Square that. Square root the whole thing. And I get 7 and I can round off with significant figures. It looks like I've got two sig figs everywhere, so it'll be just 7.7 newtons, and that is my magnitude of my net force. I'm not done, right? Every vector needs a direction. Can't just say it's off at some angle. I have to say what that angle is. So you can pick whether you want to find this angle or that angle. Doesn't matter. I'll pick this one down here. That's fine. So for that, I'm going to use the TOA. Tan theta is my opposite, so that will be the net force in y over my adjacent, which here is the net force in x. So that's going to be the 2.9183 over the 7.0812, and again, we don't worry about the sign here, so you don't get a weird negative angle. So I get the 2.9183 divided by 7.0812. And then I'm going to inverse tan that to get theta out, and I get that theta is going to be 22 degrees. All right, that is my angle. The last thing we're going to look at is how to do Sohcahtoa, or basically finding x and y components when you're on a slope. This is actually quite a bit harder than when you're on the horizontal. That's because if you have something moving up and down a hill, so I don't know, imagine this is a car or something that we're talking about here. Maybe it's driving up the hill, whatever it's doing, then if it's moving along this hill axis, it actually doesn't make a lot of sense to set your coordinate system to be the usual x is positive horizontally and y is positive up, and that's because the car is not moving in either of those directions. It's moving parallel to the hill, right? So it's going to make your physics actually easier if you can make your coordinate system parallel to one of the directions the car is moving, or whatever your object is. In other words, parallel to the hill. So it's a really good idea on hills to set x to be positive up the hill and set y to be positive perpendicular to the hill. So x and y always have to be 90 degrees to each other. That's part of just like the definition of x, y. So if you make x parallel to the hill, y is going to have to be perpendicular to the hill like this. Okay. That means that we now need to split a force like this into components. So whereas previously I looked at a force like this and thought, oh hey, this force is totally in the y direction. Now it's not, because the y direction is no longer vertical. The y direction is perpendicular to the hill. So this can take a little bit of practice, but what I'm looking for is the components of this force that are perpendicular to the hill or parallel to the hill. If it helps, you can actually turn your whole paper like this. So now my hill feels a little more horizontal and it looks like this force is off at an angle, and now you can see my y and my x are actually like horizontal in the screen. If that makes it easier for you, definitely do that. In fact, I'll do this first one like that so you can kind of see it that way. Okay, the first component needs to be parallel to y, which is perpendicular to the hill. So what I'm going to do is start at where the object hits the hill. Then I'm just going to start drawing my force component exactly 90 degrees to the hill. So try and make that a nice 90-degree angle and go straight away from the hill like that. Hopefully that's okay, kind of 90 degrees there. Then stop when you're at a point where if you turn and make a right angle, you can go parallel to the hill. Okay, so that should be a 90-degree angle here, and this component here should be parallel to the hill. I didn't do a perfect job there, but it's kind of close. So that should be parallel to the hill. This should be perpendicular to the hill. Cool. Then this component is Fy, and this component is Fx. Notice they still have arrows on them like components always do. Fx is pulling you down the hill, so this force is kind of pulling you back down the hill a little bit, right? And Fy is pulling you into the hill, so that should be this direction here. Cool. Now we need to actually calculate how big those are. So this takes a little bit of trick. I'll show you a trick though. So it's a really handy trick you can use, which is if you always draw your hills at shallow angles. So a shallow angle like 30 degrees, make it like nice and shallow. Don't draw at 45 degrees. Then you'll be able to just look at this triangle and see which is the 30-degree angle. Like, is it this one or is it this one? It's pretty obvious that it's this one, right? Like those two actually look like the same angle. This one clearly looks like a 60-degree angle, and it is. So that's the easy way to do it. The longer way to do it is actually using your geometry. So if I know that this is 30 degrees in here, then I'll show you how it works so that you can see there is actually math behind this. This is a right angle triangle. So this angle here, the angles in a right angle triangle have to add up to 180, right? So you've got 30, you have 90. What's left over? This is going to have to be 60 degrees in there, right? Then this is by definition a right angle right here, right? Because that is from the hill to the y-axis, which is by definition perpendicular to the hill. So that whole angle here from the hill to Fy is 90 degrees. This part of it is 60 degrees, so what's left over must be 30 degrees. So that's the slow but true mathy way to show that the 30-degree angle is in here. If you want to save yourself a little bit of time, just always draw your hill at a shallow angle and you'll be able to just notice and see, oh, that's clearly the 30-degree angle here. Cool. All right. Then I can calculate Fy. So I can use the same sort of Sohcahtoa as before. Fy and Fx are close to the right angle, so they're going to be either cos or sine, and we can remember the cos is close rule. So I just take the overall F, which was, I've kind of made it messy here, but it was 7.8 newtons. And then it's close to my angle, so cos of 30 degrees. I can plug that into my calculator. I get 7.8 times cos of the 30. That gives me I just have two sig figs here, so just 6.8. And using my coordinate system, this is going to have to be negative, right? Because y is positive coming out of the hill. This is pulling me into the hill, so it's got to be negative 6.8 newtons. Fx here, it's also going to be negative because x is positive up the hill and Fx is going down the hill here. It's opposite my 30 degrees, so it's going to be sine, so it'll be 7.8 sine of 30, which is going to be, so 7.8 sine 30 is going to be negative 3.9 newtons there. All right, let's do another example of that because this is a bit tricky. So here's our coordinate system. It's got x is positive parallel to the hill, y is positive perpendicular to the hill. If it helps, turn your page so that the hill is sort of parallel to the ground or you or whatever. We have to split this vector into components. So one component needs to be parallel to the hill. This is kind of a nice one because you can actually just draw that x component right on the hill itself. So I'm going to go just far enough until I can make a right angle turn and come and hit this peak here. So this is fx here, and then I make a right angle turn. This is fy. Fy is perpendicular to the hill. Notice it's going to go kind of into the hill here, and fx is pulling up the hill there. Okay, so calculating these, it's a little bit easier this time because my angle is already in the picture. So fx is going to be close, so it would be 12.2 cos of the 30 degrees. That's going to be 12.2 cos of 30. That gives me 10.6 newtons, and that's positive because it's in the positive x direction. The x component is pulling up the hill. Positive x is up the hill. Fy is going to be negative because it's into the hill, whereas y is positive out of the hill. It'll be negative 12.2, and then it's opposite my angle, so sine of 30. So that's going to be negative 6.1. And I actually need to add a 0 there just for sig figs, newtons, and we're good there. Okay. All right, let's use this to find summing the forces on a hill. So x is positive up the hill, y is positive coming out of the hill. So what that means is that F1 here is actually totally in y. But if I tilt my paper, there it is, you can see that F1 is now like straight up, like it's parallel to y. F2 is actually totally in x, it's in negative x, so it'll be a negative 1. F3 is the only one I need to split into components. So one of its components needs to be perpendicular to the hill. That's the y component. Try and make this nice and neat. Another component needs to be parallel to the hill. That's the x component, and it's kind of pulling you down the hill, so it's negative there. So here is F3y, and here is F3x. Okay, so F3y is going to be negative. It's pulling me into the hill where y is positive out of the hill. Ooh, my angles thing. Okay, so this is 25 degrees here. I can actually just see really quickly from my picture that this is going to be the small angle in here. This is going to be 25 degrees as well. But I could do it a little bit slower. I could see that this is a whole triangle right here. So all the angles in the triangle have to add up to 180. This one is going to be a 90-degree angle here. That's a right angle. I know this one is already 25, and so what's left over here must be 65. And then I can see this entire thing right here is a right angle. So from here to here is a right angle. So 65 plus something has to add up to 90. That must be 25 degrees right in there. Okay, that's the slow way of doing it. All right, so then I can calculate F3y. It's going to be negative. It's close to my 25-degree angle, so it's going to be negative 2.1 cos of 25 degrees, which is 2.1 cos of 25. Just keep lots of decimals for now, so it'll be 1.903 newtons. My Fx is also going to be negative because see how it's going down the hill, and we set x to be positive up the hill. So it's opposite my 25 degrees, so it's going to be sine, so it'll be 2.1 sine of 25 degrees, which is going to be negative 2.1 sine of 25, negative 0.88, stop at the 7 maybe, newtons. Okay. We now need to do basically everything that we did before. So from here, the problem just becomes the same as before. We split everything into components. So next we add up all the x components. So sum of all the forces in x. Forces in x, I've got F2. Right? F2 is fully in x because x is parallel to the hill, but it's negative because it's pulling you down the hill. So negative 1.8 newtons. F1 has no x component at all, right? That's perfectly in y. It's totally perpendicular to the hill. No component of F1 pulls you up or down. F3 is pulling you down though, so F3x is going to be negative 0.887 newtons. And in the y direction here, I have just two forces. I have F1 is 1.9 newtons and F2 has no component in y, right? Nothing is pulling you in or out of the hill. Then I have F3y, which is negative 1.903 newtons. I've actually set this up kind of intentionally here to give you so that when you sum up the forces in the y direction, you basically get nothing. And that's actually really common for problems on a hill. That's because usually the object is moving up or down the hill. So the forces in the y direction, pulling you out of the hill or pulling you into the hill, are going to sort of balance out. It's not really to scale in my drawing clearly here, but these forces are supposed to sort of balance out here. That's what I'm trying to show here. So in the y direction, the sum of the forces adds up to roughly 0, right? 1.9 plus negative 1.9-ish. In the x direction, they do not add up to 0. So in the x direction, the sum of the forces in x is going to be the negative 1.8 plus the negative 0.887. That adds up to, negative 1.8 plus a negative 0.887 adds up to a negative 2.687 newtons. In this case, because my net force in the y direction is roughly 0, I don't have to do a triangle and sort of add x and y together, because adding the net force in x plus basically 0 is still just going to give me the net force in x. So in this case, the overall net force just happens to be the net force in x. And that's because the net force in y is roughly equal to 0. So that means my net force is just going to be the 2 point, and I should keep just two sig figs, so 2.7 newtons. And the direction, I've left off the sign here because I'm going to state it as a direction. It'll be parallel to the hill, so in the x direction, and it'll be down the hill. All right, and that is my net force calculated on a slope.